of an ideal gas, ideal diatomic. Okay, so the first step to the problem is to so this is an ideal gas. So what do we mean by an ideal gas? We have n diatomic molecules, and they are non-interacting. Non-interacting with each other. That is, one diatomic molecule will not interact with other molecules. So that means you have some kind of a picture like this. Let's say you have one molecule here. So like this, you have a gas of this diatomic molecule, and they don't interact with each other. Okay. So, once we have this kind of a system, so we can write down the Hamiltonian. Okay. So how do you write down the Hamiltonian? Okay. Before I write down the Hamiltonian, let me first say that because these are non-interacting, what is the advantage of non-interacting? Any idea from our previous experience?
So we can treat the Hamiltonian of them separately. Like we can add them.
Yeah, correct. So Hamiltonian can be written as total Hamiltonian can be written as sum over I is equal to 1 to n and hi. Where hi is the Hamiltonian of ith diatomic. Hi is the Hamiltonian of ith diatomic molecule. This simplification will get translated into writing the total partition function to be partition function of one dipole raised to the power n. Okay, partition function of one dipole raised to the power n, where this Z1 is canonical partition function of a single diatomic molecule. Okay, so this is the advantage. You can translate this separability of the Hamiltonian into different terms in terms of the product of single. So, so it is sufficient if we can find out Z1, right? So in order to find Z1, we can write down first the Hamiltonian corresponding to one of these. So Hamiltonian for a single diatomic molecule. So the Hamiltonian for that is, how do you write this Hamiltonian? Arshad, can you tell me the Hamiltonian? Can you help me to write Hamiltonian for a single diatomic molecule? Arshad, are you there?
Yes, sir. Yes, sir.
Uh-huh. So we have a diatomic molecule like this, and then I want to write down. So this has got maybe mass m1 and m2, and imagine that this particular diatomic molecule is in gaseous state, that means it's breathing. So we have to write down kinetic energy first, right?
Yes, sir.
So kinetic energy of
I think we may have to consider the center of mass.
okay, that is fine, but let us first write down in a simple way. So let's say this is P1 square by 2m1. This is the kinetic energy of first particle. Okay, so basically this is modulus of P1 square, correct? Plus you can write down P2 square by 2m. And is there anything else?
I think the interaction between M1 and M2.
So there can be some interaction, and that interaction will depend upon R1 minus R2, because that is the separation. So this is our what is called the total energy Hamiltonian for a diatom. Now you can think of writing this in different ways. But before we do that, let us try to understand. Uh, our aim is to find the specific heat, right? So, is there a simple way to find the specific heat without doing any calculation? Is there any simple way? So the question is there a simple way to guess PV without doing any calculation? Our guess may be wrong, but it is better to make a wrong guess than not guessing at all. So I just want to know, is there a way to guess?
So we can reduce the degrees of freedom here.
Yes. So what does that tell you about the degrees of freedom?
So instead of 3n,
So
we can reduce to some number. So M1 and M2 are connected, and if the
let me
final
write.
expression, we can replace that n value with a new n value.
Yeah. So let me first write this potential in a general form like this. Okay, so it will depend on R1 and R2. So first let us write that it depends on both R1 and R2. Okay, so like one of the possibility of guessing is just enumerate number of degrees. Okay, so how many number of degrees of freedom are there, and More importantly, enumerates number of degrees of freedom that enter H quadratically. Why is this important? Because if we can find that, then we can use equipartition. Correct? Equipartition theory. Okay, so how many degrees of freedom are there such that there is a quadratic representation of those degrees of freedom in the Hamiltonian? Now you see that you have P1 square will have three quadratic terms, that is x component of P1, y component of P1 and z component of P1. Similarly, P2 square will also have three components. So totally how many components are there? There are six components here. Okay, there are six components associated with this. Now, this is one way of looking at it. Or just because you already know that there is some kind of a diatomic molecule. Okay, so diatomic molecule like this. Now you say that there are two particular so this is diatomic molecule is placed in 3 dimension. Okay, so then each one will have three coordinates. This will have three coordinates. Okay, so now you can see that if you can decompose this as some kind of a center of mass, then the position, then the center of mass will require three coordinates to move around in 3-dimensional space. And then there are two rotational degrees of freedom. There is no rotation around the axis of the diatomic molecule. So there will be 5 degrees of freedom, translation plus rotation together. Then there is a vibrational degrees of freedom. So vibrational degrees of freedom, that means this, if it is a rigid rotator, that means if this bond connecting these two masses are rigid, then you have only 5 degrees of freedom. But now, if this is not rigid, now you can see it is not rigid, even though I have drawn like this. Now this is like a bond. So bond can be modeled as a kind of spring. Okay, so this is rigid, and this is non-rigid. So if it is non-rigid, then this is like a harmonic oscillator. So this harmonic oscillator will have 2 degrees of freedom that enter into the Hamiltonian. So totally the number of degrees of freedom, so degrees of freedom is 3 translation plus 2 rotation plus 2 degrees of freedom that are coming from the vibration. So you have 7 degrees of freedom. So by a blind application of equipartition theorem, we get from application of equipartition theorem, that we have average energy to be 7 into half K. Correct? So then your CV will be equal to average energy, that is by, that is equal to 7 by 3. So this is basically the specific heat per part. Okay, specific heat per part. So this is kind of a simple estimate of the specific heat per particle of a diatomic gas. Now, because they are non-interacting, the total specific heat is simply 7 by 2 times n kb. That's all, because that just gets added. Now, one can ask a question that you want to. So this is just a kind of a estimate by using equipartition. Now you could have actually calculated this from using our classical statistical mechanics. So let us say that let's try to write this diatomic molecule, decompose this just like what you know, that this in a two-body problem, you can always represent a center of mass coordinate and then a relative coordinate. So you can write down your partition function, just like we have seen that the partition function can be written as product of partition functions for each one of the molecules. We can also write down Z1 itself. Okay, we can write down as the partition function for translation multiplied by partition function for rotational degrees of freedom multiplied by partition function for vibrational degrees. Actually, there is another possibility. There can be a partition function for electronic degrees of freedom. That is electron degrees of freedom inside this molecule. Okay, so now depending on our temperatures or depending on the energy that is available for the system, whether electronic excitations are taking place or not. If electronic excitations are not taking place, that means for all practical purposes, electron in each of these atoms is in the ground state only. Then we can forget about this. That means the thermal energies involved are not high enough to cause electronic excitation. Okay, just to get an idea, for example, if you take hydrogen atom, okay, you have ground state energy. Ground state energy is minus 13.6 electron, and the first excited state energy that is E excited is minus 13.6 divided by 4 electron. So the difference is EE minus EG is equal to minus 13.6 into 1 by 4 minus minus 1 is equal to minus 3 this is plus, so 3 into 13.6 divided. So that means it is 75% of this. Okay, so let us say roughly it is about 9 electrons. So to excite an electron, in hydrogen atom, uh, we need temperatures such that your kBt is of the order of 9 electrons. Now you can verify that this implies that T should be greater than some 10,000 Kelvin, okay, or maybe more, 20,000 Kelvin. I don't know. This is just of the order. That means if we are talking about temperatures which are less than 10,000 Kelvin, then we can ignore the contribution from the electronic Hamiltonian or the partition function for the electron. So I'm going to assume that I'm not going to do any calculation or experiment with the diatomic gas, which is having a temperature of this magnitude. So I am going to ignore that and then concentrate only on these two. Okay, so the translation degrees of freedom are associated with the center of mass of the So let's try to look at how to do this translation partition function. So the partition function for the translational degrees of freedom is at T. Now we are the center of mass of this diatomic molecule will move as if it is a free particle. So we are going to have a integral that is 1 over h cube into integral V3 of R, center of mass position, and V3 of B, center of mass momentum, and e to the power minus p square by 2m. This is the total mass of the system. Now you can see that this integrand does not depend on the position. So the position gets integrated. So you will get a V out. So V by h cube. Okay, V by h cube. And then you have this integral over d3. So whenever you have this kind of integral, so you can see that integral over d3p, which I can write it as simply integral over p into e to the, of course there is a beta here. Please note that it is e to the minus beta. the minus beta E square by 2m. So this is one component, and that will be raised to the power, because every component will have the same. So this is equal to, this calculation is exactly same as what we did in ideal gas. So this is a Gaussian integral, and so 2m I divided by theta raised to the power b. Okay. Now this you can actually remember that it is very easy to remember this and write, because we
Sir,
have to.
sir,
Yeah.
sir, that should be capital M, no? Two capital
Huh?
M, sir.
Uh-huh.
Two capital M.
Yeah, yeah. This looks carefully. So you can see that this is equal to, I can write this as B divided by B, because your VQ is H square divided by 2 pi m ABP raised to the power 3. Now I want you to just remember that whenever you have a momentum integral, okay, this just kinetic energy integral over momentum with this 1 by h cube, you will always get this VQ or lambda cube, whatever. VQ or lambda cube. This can also be written as V by lambda. Okay, so we don't have to do this again and again. We can remember this result and then simply write whenever we require. So that means we have now completed our calculation of the translation. So what is that? Our Z translation is equal to V divided by B. Okay, so now let's look at Z rotation. So let's look at Z rotation. This rotational partition function. So you have 2 degrees of freedom associated with that, and usually the rotational degrees of freedom are some angles. Okay, so the corresponding canonical momentum will be some angular momentum. Okay, so we can have a situation like this. Z rotation can be written as 1 over h square. Why h square? Because there are only 2 degrees of freedom. Into integral. So there is some angle which I will call it as some theta, and there is a angular. There is a momentum associated with that. There's an angular momentum associated with that, which I will call it as dp theta. And then there is another angle probably, which I will call it as phi, and another angular momentum which I will call it phi. And then the energy is simply e to the minus beta p theta square by 2 2I into e to the minus beta p phi square by 2. I is some moment of inertia of the system. So this is the kind of integral that I have. So now this angular part of the integral is going to give you some constant about the theta and phi, because you see this this integrand does not involve theta and the integral does not involve phi. So we can get some 2 pi and 2 pi from there. So let's call that as one can be more rigorous, but we are not very much interested in these constants. Let's call this as 2 pi square divided by h square. Now this integral is exactly same as the Gaussian integral that we have talked about earlier. So we are going to have 2I by beta, one integral over p phi, and then square root of 2I. So this is equal to, you have so I'm going to write this as some constant involving all these 2I etc. h cubed, and the only contribution that I write is beta is separate. Okay, so I can do the same thing here. Here I can write this as there is some constant at. Okay, so divided by beta to the power 3 by. Okay, I can write it like that. That is, other than beta factor, everything else I am dumping in this constant a. Same thing here. So I have my ZR as some constant AR divided by B. Now let's look at vibrational contribution. Okay, so namely Z vibration, vibration so you have for this vibrational contribution there is so now if you look at this vibration, will have let me write down, Z vibration will be like 1 over h integral. I have d3r and the corresponding momentum, which I will call it as lowercase p, into e to the minus beta p square by, of course, you know that if you are using relative coordinates, you have to use some reduced mass into the, this is how you reduce a two body problem into one body problem, into I have e to the minus beta into this v of r. V of r. So once again, this particular kinetic energy integral will give you, so you can see that this integral is this is the first the integral can be written as 1 over h, and I can do this integral, then I'll get twice mu by beta under square root. That is for the kinetic energy part, and of course I have this d3 r into e to the minus beta. Now this can be written as 4 pi r square. I can write, because this v depends only on r, so I can write this as 4 pi r square dr. Okay, so I can replace this with this, and so here let me say that we have a situation that we are going to look at small oscillations, from equilibrium. That means I can say my R is equal to some R naught plus some eta, and where this eta can be very, very small. So then, because of this consideration, we can say that my V of R naught plus eta can be written as V of R naught plus dV by dr evaluated at R is equal to R naught into eta plus d square V by dr square evaluated at R is equal to R naught with eta square by 2, and so on. And I can neglect all these higher order terms, can be neglected. Since eta is much smaller than 1, and this particular term is 0 since R naught is equilibrium length of the spring. So at equilibrium length there is no force, and UADR is the force, and we will this particular term is a constant, so you can always absorb as reference. Okay, so as a result, what happens is that if you are going to look at this, this will be equal to 1 over h and square root of twice mu by beta, and we have some 4 pi and integral r square. Okay, so you can choose this eta as your coordinate now. So then you can write this as eta square eta into e to the minus beta into half k eta. I think I have written this in a very clumsy way. Let me write it again. So what I am trying to do is,
So is that 1 by h or should be 1 by h square? Because we have considered 2 degree of freedom for vibration.
No, it is 1 by h only because these 2 degrees of freedom are conjugate pair. Correct. R and P are conjugate pair. For
Okay.
every pair, I will have 1 h. So that is equal to, let me write down 1 by h and square root of twice mu by beta and 4 pi and integral d eta square and e to the minus beta k eta square by. Now here I am writing this k as d2v by dr2 evaluated at r is equal to r. This is like the force constant of the spring. Okay, so now you can see that this will be from integral is from 0 to infinity, and we can, apart from some factors, you can see that this will be like this is like a gamma function. So you use this result that use this formula, that integral 2 times 0 to infinity of dx and x to the power 2p minus 1 into e to the minus x squared is equal to gamma. So if you use this relation of a gamma function, then you can solve this integral. So what do you get? You get oh sorry, I think I made a mistake. Let me correct it. So as you see here that this is not d3r. Okay, this is only this v of r. So I think we should not write this as 4 pi r squared here, because this is just a radial coordinate now, because angular part is already integrated. Okay, so this is, that means this eta square is not there. Eta square is not. So then I don't require to use this gamma function. Okay, so this is not required. Not. Okay, so now you can see that you will get head vibration will be some A vibration. Okay. Already there is a beta sitting here, correct? And here you will get so the integral, this integral will be square root of 2k, sorry, 2 by k beta. This is what you will get, square root of 2 by k beta. So here you are going to have this to be A vibration divided by beta, because there is one beta square root of beta coming from here and one square root of beta coming from here. So if I now write down the full partition function,
Sir, root over 2 pi by kb should be, no?
yeah, there is a so now if I write down the partition function for one diatomic molecule, which is translation, rotation and vibration. So you can see that there is some constant which I will call it as AT multiplied by AR multiplied by A vibration. Okay. So you can understand why I'm not interested in this, because I'm not interested in uh, this constant, which does not depend on temperature. Then the translation part has got 1 by beta to the power 3 by 2. Rotation has got 1 by beta, and vibration has got. So this is like we have some constant. I will just call it as A1 divided by beta to the power 7. Okay. So now you ask what is the average energy? Average energy of the system is minus uh, del by del beta of logarithm z is equal to minus del by del beta of logarithm of A1 minus 7 by 2 logarithm of. So A1 does not contain beta, that is why I was not very much worried about what is A1. And this one is 7 by 2, 7 by 2 into 1 by 2. So that is, we are right from our estimation of equipartition theorem. So we have 7 by 2. Then, of course, Cv is equal to the derivative of this energy with respect to temperature, which gives you the specific heat per particle to be 7. So this is a classical calculation that we have done, and what you experimentally observe, and so ultimately what happens is that you have to now check with the experiment. Okay, so what is it that we are getting here? We are getting so if you plot temperature versus Cv by N, so we are getting a value is independent of temperature. So this is our specific heat result, and this value is 7 by 2. So this is what we have. Of course, we have looked at it from equipartition theorem as well as from the classical statistical mechanics calculations. Now, if you do an experiment, then what one observes is that the experiment has an interesting result. Okay, so let's. Okay. So experiment will show this kind of 7 by 2 kT at a very high temperature, and then at some temperature it deviates from that, and then comes to this curve, and then it remains with this curve up to some temperature, and then it again falls off. Okay. and this is 5 by 2 kb, and this is 3 by 2 kb. So this red curve is this is what experiment. Experimental. So this smoothly goes. I did not draw it very nicely, but please understand that this smoothly goes from here. Now, so how do we understand? Okay, we know that we have done classical statistical mechanics, but we did not get the correct result. Uh, that is agreed by the experimenter. So, any suggestion? What should we do, and why is this happening? From the statistical mechanics that we have understood so far, is there some? Can you reflect on some? Yeah.
Sir, at very low temperature, I think we can treat them as a rigid body, and in that case, the degree of freedom is reduced. That's why I have 3 by 2 kBt at very low temperature, but don't know about the 5 by 2 kBt.
Okay, so I think you can. Okay, so before I discuss further, are there some other opinions? Now, when we are saying that okay, we are doing theory, it doesn't mean that I can explain 3 by 2 kBt, 5 by 2 kBt, and 7 by 2 kBt, but I also should explain how it comes from 7 by 2 to 5 by 2. That means, if I derive an expression for specific heat, it should also explain me this variation those temperatures where it is falling from 7 by 2 to 5 by 2 or 5 by 2 to 3 by 2. That also I should be able to derive an expression which represents this variation. Okay. So one of the things that I think what Abhijit rightly pointed out is that maybe there is, just like what we discussed with respect to electric excitations, maybe there is some temperature at which thermal energy is not enough to excite even vibrational excitations. That means the system is settling in the ground state of the vibrational area. And there exists another temperature at which the system is not even able to excite the rotational excitations. Then you have only 3 by. That means if you have 7 by kBt and then suppress, of course, the technical word it is called is freeze vibrational degrees of freedom. That means freeze vibrational excitations. Then you get 7 by 2 minus 1, that will be 5 by 2, and then freeze rotations, then you will get 3 by 2. That is fine. I can understand that within this temperature range, it should be 5 by 2 and 3 by 2. But then we should also understand how to get the behavior of this functional form, that it should go from 7 by 2 to 5 by 2, 5 by 2 to 3 by 2, according to the curve that experiment is giving us. Okay, so this is what is the task, and it is very simple. We can. This also is a very rich physics with respect to this calculation. So now what we are trying to do is that at very high temperature. Okay, so at high temperature, CV by N is equal to 7/2. Okay, according to classical calculation. But then there is some temperature. So at some temperature, CV by N deviates from 7/2 kb, 7/2 kb, and settles to 5/2 up to some temperature. Now this can be understood. This can be understood. This can be understood from freezing of vibrational degrees. Now, please understand that freezing, the concept of freezing is somewhat like what I said. So, what do we mean by freezing? This freezing implies that thermal energy is not high enough to excite the diatomic molecule from its vibrational ground state. Now, we know from spectroscopy that vibrational energies or vibrational degrees of freedom require high energies. If you look at spectroscopy, like IR or UV visible spectroscopy, it is the vibrational levels that actually contribute to these transitions. If you are looking at rotational levels, they are usually used in the microwave region. So that means they require less energy. So if you are decreasing the temperature, the first degrees of freedom that will be frozen are vibrational degrees of freedom. But now we are interested in asking what happens to the specific heat as we go from 7/2 to 5/2. Okay. First, recognize that since we are saying that you have a ground state and excited state, etc., so we should not work with energy changing continuously. So acknowledge that fact that we have to now work with the quantum mechanical energy levels. Okay. So recognize that we have to work with, we have to work with discrete energy spectrum of the oscillator. And so we know that oscillator has got energies En is equal to n plus half into h bar omega. And so what will be your vibrational partition function, which I earlier did it in different way, is now should be written as sum over n is equal to 0 to infinity e to the minus beta h bar omega into n plus half. Okay, so I don't want to do this calculation because we did this calculation earlier. So dot 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 dot. So if you do this, then you will get a contribution for CV of vibrational contribution. Vibrational contribution turns out to be something like this. So there is some temperature which you call as Einstein temperature divided by E whole square into e to the power minus beta E by B. Okay, under the assumption that that is in the limit h bar omega is much greater than k. In this limit, you have something like this, where you have this theta E is what is called the Einstein temperature, which is given by h bar omega by Boltzmann constant k. Now, what happens? So now you have. So if you look at your if you look at this particular transition, okay, so you see this particular transition. So let me just draw this. This is your 7 by 2 dV by n. So this is your 7 by 2 kb, and let's say this is your 5 by 2. 5 by 2. Okay, so now what happens at some temperature? Okay, so here you have a temperature of the order of theta E. So around that, up to much above the theta E, it is going to be like this, and then around that theta E, the deviation will start. Now, exactly following this functional form, the deviation will decrease like this and join here. So much below this theta E, it will be 5 by 2, because now no longer this vibrations will contribute to the thermal excitation any longer. But this particular, so this exponentially falls from 7 by 2 to 5 by 2, and that is what is given by this Einstein's expression for the specific. Okay, so this is good. So we have used some knowledge that we have already obtained from our Einstein's theory. Now, what about rotational degree separation? That is how this comes from. So at much lower, at further lower temperature, So T CV by N deviates from pi by 2 kV and settles 3 by 2. Now, why does this happen? This happens because um, at these temperatures, rotational degrees of freedom are frozen. Rotational degrees of freedom are frozen. That means thermal energy is not enough to excite the system from the rotational ground state. That means we require to use angular momentum, that is rotational energies. So, so the discrete energy for the rotation. Okay, so we have our Hamiltonian for the rotational part is given by some kind of j square by 2I. This is the free Hamiltonian, and that is equal to the energy levels will depend upon j, which is given by h bar square by 2I into j plus 1, and this j will go from 0, 1. Okay, so this is essentially a classical orbital angular momentum, even though I am using j here. So this is these are the energy levels, and but note that note that j and jz commute. In fact, they are called CSCO, complete set of commuting observables as far as this is concerned. And you can see that there is a degeneracy. So every EJ EJ is 2J plus 1 fold degenerate. J plus 1 fold degenerate. So how do we find out the rotational partition function? The rotational partition function now can be found out by taking sum over j is equal to 0 to infinity. So I have 2j plus 1 as the degeneracy or the multiplicity of each energy into minus e to the beta h bar square by 2I j into j plus. So this has to be evaluated. The sum has to be evaluated. Yeah. So this is what we have to do. But now the point is that it's not very easy to evaluate this sum. Like in the previous case, we had an advantage that that sum was a nice geometric series, and hence we could sum that. But here there is no, it is not a very nice sum, so we can't get a closed form expression. but we can make progress. So we can make progress, and writing this as, suppose if I take j equal to 0, I have 1 plus, if I take j equal to 1, I have 3 into e to the minus beta h bar square by 2I into j equal to 1, so this is 2, okay, plus I can have this infinite series, and I can use this infinite series, and I can write down simply using this infinite series itself. I can write down average energy as minus del by del beta of logarithm z half. So the average energy, and CV for the rotational contribution can be obtained as minus uh, average energy for the rotation divided by. I can get an expression like this. It will be infinite series, but if temperature is very small, then beta becomes large. Then because I have e to the minus beta, these terms become smaller and smaller as you go in the higher and higher terms in this series. So I will be able to truncate the series at some point, such that I will get experimentally observed result. So just like the CV vibration that we have defined, derived using Einstein's theory, this also we hope that is what gives you this transition, that is a crossover from 5 by 2 to 3 by 2. And it is indeed so, because that's how the rotational levels will be frozen. Okay, so I will leave it as an exercise for you. That is, let's say that you keep only up to this. Okay, so neglect all this, and then calculate this. Calculate, and then you can define some rotational temperature below which you can see that 3 by 2 is the proper specific heat, and there will be a crossover from 5 by 2 to 3 by 2 around this theta r that you are going to define. Okay, so we have managed by invoking this quantization of the energy levels, and then we have explained why this crossover happens, because of the freezing of these degrees of freedom. That means they will settle on the ground state of corresponding. But the story is not end, because when we try to look at it again from the experiment, there was a surprise, and the surprise is something like this. So let's say that now let me just concentrate on let's say this is T and this is CV by N, and let's call this as pi by 2. So let me write down CV by N kb. So this is 5 by 2, and let's say this is 3 by 2. This is 5 by 2 and this is 3 by 2. Now when you actually do this theory, okay, so as I have told you earlier, I just mentioned in the previous case, you have an experimental curve which is like this. So this is this red one is experiment, and I am supposed to get theory also agreeing with this. Which theory? This theory. So if I use this theory, then it should agree with. But what is observed is a small deviation from this result. For example, if you consider the theory, that we have uh, goes like this, and then it goes up like this, and then comes down. Okay, so this is here. Okay, this is theory. Which theory is actually this theory? This theory gives you a kind of hump. Okay, and it agrees with this one at a much lower temperature, but at this point there is a deviation. And of course, you have to. I have to make this remark carefully, because the theory and experiment. So theory and experiment they seem to disagree for uh, H2 gas. Okay, specifically when people looked at H2 gas, then they found that theory and experiment disagree. The disagreement is exactly like what I have done here. Theory gives you some kind of a hump here and then falls, whereas experiment has a continuous fall. Okay, so now we have to understand why this is happening. So for that, what we should see is that uh, in hydrogen gas. Okay, so in H2, you have one hydrogen atom and then other hydrogen. And these two hydrogen atoms are this and this, they are identical. Okay. Now this has got the nucleus of the hydrogen atom has got spin half. And this also has a spin half nucleus. So because of that, what happens is that this when it becomes a hydrogen molecule, so you have it is like addition of two spin half particles. Okay, so S1 is equal to half and S2 is equal to half. Then the total spin, okay, S of H2 molecule, will have 0, 1. This is addition of angular momentum. Okay, so when S is equal to 0, okay, so when S is equal to 0, this is called I do not know. I always get confused. I think this is called ortho state, and when S is equal to 1, it's called para. Okay, so you have ortho state and para state, but note that because they are identical, since they are identical, the total wave function of hydrogen atom, hydrogen molecule should have an antisymmetry. Okay, so that is uh, the total wave function should be antisymmetry. Okay, now we are actually going to proper, deep quantum ideas. Now the point is that because we are looking at when the vibrational degrees of freedom are already frozen. Okay. Now when you look at S is equal to 0 state, okay, S is equal to 0 is a spin antisymmetric state. Spin antisymmetric. This is a singlet state. Spin antisymmetric. That means your spatial wave function should be symmetric. Only then the total wave function will be antisymmetric. Okay. On the other hand, if you take S is equal to 1, then this spin state is symmetric, plus triplet state. So spin symmetric. And that implies that your spatial wave function should be antisymmetric. Okay. Now look at spatial wave function. Electronic wave function is in the ground state because that is already frozen. So that is symmetric. Vibrational ground state is symmetric because it is also in the ground state, and you don't have the translational state is always symmetric. So the symmetry of the wave function will be determined by the wave function of the rotational state. Now you can see that the parity of so you can see that parity of rotational wave function. I want you to remember that these rotational wave functions are spherical harmonics. Is simply -1 to the power. So that means if you want it to be symmetric, then J has to be even. If you want it to be antisymmetric, then J has to be odd. So because of this, what happens is that you should find out two different. So your Z rotational. Suppose if you take S is equal to 0, that means let's say you have ortho hydrogen. Then you have to calculate your ZR to be sum over J. Okay, sum over J, and you have only even into 2J plus 1 into e to the minus beta h bar square by 2I into J plus. Okay. And if S is equal to 1, and this is your para. So I don't know, maybe I should call this as ZRO and this as ZRP, and that will be same, but this J will be over all RJ 2J plus 1 into e to the minus beta h bar square by y j into j. So you can calculate this one separately, and then you can ask. So what happens is that the so you can see that s is equal to 0. S is equal to 0 is just one state, because your ms is equal to 0, whereas s is equal to 1 is 3 states, because your ms can be -1, 0, and 1. So typically, if you have let's say a collection of n hydrogen atoms. Okay, so let's say you have n hydrogen atoms. So n number of hydrogen atoms if you have, then at any temperature there will be some it is like 1/3 of 1/4 of them, 1/4 of them in ortho state, and 3/4 of them in para state, because there are more 3/4 of them in the para state. So what you can do is that you can calculate your CV by n. You can call it as nkb as 1/4 times CV by nkb associated with ortho plus 3/4 times CV by nkb of this para. Okay, so when you do this calculation, how will you calculate this ortho? You calculate by using the partition function that we have used by summing only even j, and para you sum over only odd j, and then you find out the average energy and then calculate CV, and then obtain the CV as a weighted sum of both ortho and para. Now it turns out that when you do this, you can get a result which agrees with the experiment. That means that hump will not be there if you calculate your CV by NB not as sum over all j, but you take sum over even and sum over odd separately and calculate them and take their weight in this fashion, then you will get this. Now this particular thing is so there is someone called Denison. Okay, so this work was done by someone called Denison in 1927, where he showed that the specific heat for hydrogen, whatever deviation from the theory, can be explained if you use this kind of a ortho. That means already the identical particle nature of hydrogen is incorporated, which comes only in quantum statistical mechanics. But this is one particular experimental situation where the quantum statistical considerations are required. Already the identical particle nature of the hydrogen atom is important. Now one is also interested in asking that can I change this population, that is 3:1, this kind of a population, can I change? Now it turns out that if you pass the hydrogen gas, okay, so Denison observed that if you pass, so if H2 gas is passed through an activated, I do not know the mechanism, but they observed that if it is passed through an activated charcoal, then the population of ortho and para can be changed, can be altered. So Denison did a kind of systematic experiments, and then where he showed that so if you want to get this, so let's say you have some R, some kind of a ratio which you can so NKE so plus 1 minus R into CV by NKE of para. Okay, so now this R can be fixed. Okay, so this can be controlled by using the temperature and the time over which H2 gas is passed through the activated charcoal. And then so now after you do this, you remove this charcoal, then you have this hydrogen gas with a different population. Now you can do an experiment and also do theory and compare. So this series of experiments have been done by Denison, and then he established that this is the correct way to get the experiment and theory consistently correct. Of course, he also experiments with this is again a nice example as how to just getting one result. You should not be satisfied. You should establish. So he also did this experiment with, for example, D2. This is called heavy hydrogen. And then he found that results are same, so you get the same result. And then he did these experiments with HD. That means one is hydrogen and the other is deuterium. Okay. Then you see that you don't have this. So result is now consistent with getting your partition function z rho by summing over all j. 0, 1, 2. You don't have to now do even and odd. So whatever hump that we have seen will also come in the experiment when the two of the diatomic atoms are different. One is hydrogen and the other is deuterium. So this feature that deviation from the sum is a consequence of the identical nature of these two atoms. Okay, so this is kind of a very nice problem where we started with classical theory, and then we found that the freezing can be understood only when you bring in quantization of the energy levels. Okay, but we still did classical statistical mechanics, and then finally when we are looking at crossover from 5 by 2 to 3 by 2, then we have a deviation when you have diatomic gas with identical atoms, and that is because of the symmetry properties of the wave function. And we can see that the symmetry properties of the wave function, when you calculate this appropriately, you will see that you get the correct experimental results born out of the theory if you are using partition functions calculated based on the symmetric and anti-symmetric requirement of the spatial wave function. So I think I'll stop here, and if there are questions. This is an interesting problem. I like this problem because it actually demonstrates all the techniques that are required to understand statistical mechanics.
Hello, sir.
Yeah.
Hello.
Yeah. Go ahead, Krishna.
So I could not understand that ortho and para concept.
That is, if you look at hydrogen molecule, so if you look at hydrogen molecule, so let's say that you have understood the addition of angular momentum. Suppose if you take S is equal, S1 is equal to half and S2 is equal to half, then the total S can range from modulus of S1 minus S2 to S1 plus S2 in steps of 1. Okay, so because of that, this S becomes 0 and 1. Correct. So if you are saying that you have two spin half particles, here this is hydrogen nucleus and hydrogen nucleus. These are two spin half particles. Now the total spin of the hydrogen molecule will be either 0 or 1. Now you can say that if S is equal to 0, then your MS will be equal to 0. That means in this state you have simply 0, 0. There is only one particular state. On the other hand, if S is equal to 1, then your MS can be 0 or 1 or minus 1. That means you have three states: 1, 1, 1, 0, and 1 minus 1. Okay. So what we do in quantum mechanics, you call this as a singlet state. Singlet state. And this is called a triplet state. Okay. So this so if your hydrogen atom is in this spin state, that is, if spin state is this, then you call that as orthohydrogen. And if it is a triplet state, then you call this as a, this is spin state. But the total state, you know, in quantum mechanics, the total state, suppose I call this as psi, the total state is equal to, you have some spatial state, spatial wave function, and then there is some spin state. Okay. Now for singlet, this is antisymmetric. So this has to be symmetric. Only then the total wave function will be antisymmetric. Correct. This is for singlet state. Singlet or orthohydrogen. Whereas for triplet state, this is symmetric and this has to be antisymmetric, so that the total wave function once again is antisymmetric. Total wave function is antisymmetric. This is for triplet or para. Okay. Now the question is, how do I get this this one as symmetric or antisymmetric? Okay. So that is by saying that the angular momentum, okay, for this case, J has to be U. J has to be U. And for this case, J has to be R. Has to be R. So this is what we learn from identical particles, are the theory of identical particles in quantum mechanics. And because of that, my summation has to be done accordingly to get the partition function for parahydrogen or orthohydrogen. Okay. If I have to make it more clear, then I have to teach addition of angular momentum completely, which I think I cannot do it now. So please look at addition of angular momentum, how this triplet and singlet state comes.
Okay, sir. Thank you, sir.
Yeah. Any other question?
Sir?
Yeah.
So in case of sir HD molecule, we have this hump in the experimental result.
Yes.
Okay, sir.
Any other question?
Sir,
Yeah.
the hydrogen molecule, is it a boson or a fermion? That's like
Hydrogen, no, hydrogen molecule, whether it is a fermion or a boson, it depends on at what level you are asking this question. So if you consider spin of nucleus, spins of the electron, all of them put together, it will be if it has an integral spin, then you can call that it's a composite boson.
okay. So it has two nucleons and two electrons, right, as a whole.
Yes.
So it should be a boson, right, because it will be an integral spin.
It's not like that. See, if you take two hydrogen molecules, then you can consider each one of them as a boson. But you are getting hydrogen molecule by taking two hydrogen atoms, correct?
Yeah,
So
yes.
each of that is a fermion.
Each
You
hydrogen
understand?
atom is a fermion.
Suppose if you take one H2 molecule and another H2 molecule,
Okay.
and then write a two-particle wave function for two H2 molecules, then it will be symmetric because each H2 molecule is a boson. But if you take one H atom, other H atom, then write H2 molecule wave function. Since each H atom is a fermion, the total wave function has to be antisymmetric.
Okay.
See, you will get the same doubt for two electrons. No, when you write two electron wave function, we are demanding that it should be antisymmetric, right?
Yeah,
Two
yes.
particle wave function. Same thing here.
Okay, sir. Okay. Sir, can you explain that partition function for that vibrational motion?
Which stage? The quantum mechanical stage or
In the beginning, like first one.
here?
Ah, yes, yes. Like it is having 2 degrees of freedom, right?
Yeah, yeah. So essentially, that's what I think. I made this mistake initially. So I should not write this as dq.
Two p.
Simply one variable, that is radial coordinate and radial momentum. So that is why I corrected it here, but it is simply dr and dp. Then dr becomes d eta because of equilibrium situation. This is exactly what we do in small oscillations. Okay, so what we are saying is that you have this spring, and equilibrium length of the spring is some r naught, and when you when you apply some heat at some temperature T, then this r naught will change to r naught plus. So let's say this get extended a little bit, and then this is what we call as eta. And this eta is dynamics, and the dynamics is like harmonic oscillator because whatever is your potential, very close to equilibrium, you can expand it and show that if eta is small, then it will be like half k eta square. So you will have a harmonic oscillator like potential. This is the crux of small oscillations. No? In classical mechanics, we study something called small oscillation.
Yes, yes.
Close to equilibrium, the dynamics is always governed by harmonic oscillator like potential.
Sir, then here 4 pi terms shouldn't be there, right?
Yeah, this should not be there. But I don't think you should worry about it because I am only looking at beta part here. But strictly speaking, you are right.
Yes, sir.
Sir?
Yeah.
So we consider harmonic oscillator here, but in practical, in practice, the oscillations are not always harmonic. Like anharmonicity is there, so we didn't consider anharmonicity. But we get the experimental result fit with the theoretical prediction.
That is, you're asking instead of taking harmonic, if you take unharmonic term, will we get the
Will we
deviation?
get the different result? Will it match with the experiments?
Yeah. I do not know about such calculation, but one can do this and check, but I believe that the deviation from 7/2 to 5/2, that curve will not be reproduced by such receptor, because that curve is exactly reproduced by this Einstein expression for the specific heat. But you may have some deviation from the because you know that the moment you put in some anharmonic terms, there is going to be decrease in the energy, thermal energy, and there is going to be some decrease in the specific heat. For example, we discussed last time, if you have a potential which is like x power n, then the share of average potential energy will be kT by n. So it's not kT by 2, but you have some smaller energy contribution for higher powers, and hence there will be some decrease in that. So there will be deviation from 7/2, but we will not have a match with the experimental result.
But sir, in practice, like in reality, the oscillations are anharmonic, no? Because it is easy to not so easy to compress the molecule, but to expand it is easy to expand the molecule.
That is correct. But what we are saying is that these things are not happening at a very high temperature, and so classically, it makes sense to talk about harmonic variation. Still, that seems, because remember that when we are going to low temperature, are trying to understand this deviation from 7/2, we are still making it harmonic only. Only thing is we are saying that the energy is no longer continuous. There are discrete energy levels. Okay, so unharmonicity comes usually at a high temperature, a very high temperature, and then after you get this unharmonicity, then you have only melting after that, kind of a melting takes place. That means bond breaks.
Okay, so dissociation of.
Yeah.
Okay, sir. Thank you, sir.
Okay, so I think I wanted to just initiate this idea that now we have covered canonical ensemble, I think, in all its completion. So I think we have completed 2 units. So it is good that we should start thinking about form and the format in which we should conduct it. All that I think we have to discuss. I don't want to discuss now, but I just wanted to put this idea across so that you people can also start discussing and thinking. I don't know if you have already written some exams for other subjects, but we have to do something in the month of November. So one internal exam should be written. So how to write it and what to do, we have to evolve collectively, then decide a format and form of the exam. So think about it, and maybe in the next class we will. So if this is done, then Ruti, we can close.
Okay, sir. Thank you, sir.